So if you recall, last time we had talked about how to implement the Memoizer with a FutureTask, and we talked about how cool that was, even though it's probably more complicated than you would want to do if you can program with newer versions of Java. So what we're going to do now is take that updated Memoizer class and apply it to the PrimeChecker app to see whether numbers are prime. This is going to look very familiar to you. Really, very little has changed. It's still embarrassingly parallel and compute bound. We have a main activity, which is going to use a fixed thread pool this time, again, just for kicks, just to be mixing things up a little bit. We tune that to the number of processor cores, so this will basically, maximize the utilization of your CPU by running on all the cores. We'll use our Memoizer, as we talked about before. We'll see where that fits in a second. We have the prime callable class, which implements callable, so it's got this two-way semantic, and we can submit this to the ExecutorCompletionService framework. The constructor stashes away this PrimeChecker function, which of course will be implemented as a Memoizer, as we'll see in a second. The call method will apply the PrimeChecker function on the prime candidate, which again really depends on what's passed in to the prime callable class to dictate what the behavior is going to be. And we can transparently optimize all this by using the Memoizer, and it returns the prime result. Here's really the main activity logic when you start the computations. We have a Memoizer, which is going to cache the results in the hash map. And you can change the PrimeChecker. You could make it some other PrimeChecker besides this one. You could make it efficient PrimeChecker or whatever. We generate range of longs between a certain value set, so we get duplicates. We convert those long random numbers into prime callables, passing in the Memoizer. So it'll optimize it transparently. That's like super cool because this code doesn't really know or care that that optimization is being done. It works just the same way as it did before. And then the last thing we do is we go ahead and we submit this code. And one of the nice things about using the executor completion service rather than using the executor service is we don't have to keep track of the futures ourselves. The futures are not tracked by the client code. Instead, they're tracked by the executor completion service and its completion queue. So it just makes things a little cleaner, a little neater. We still have to have a thread running in the background, however, that will wait for the completed results to finish so we can count them and see that they all worked, or if they worked. And so to do that, we go ahead and we make a new thread, giving it this runnable, and we start the thread. Here's the completion runnable, which is a runnable, which means it has a run hook method. It iterates from 0 to less than m count. And every step along the way, it calls the take method on the completion service, which, as you recall, will block until there's some completed result. And whatever completed result gets done next, we'll get that. And then we call the get method on the future. And that, of course, will not block because it wouldn't go into the internal completion queue unless it had completed. So take may block, but get will never block once you've got a future at that point. And then we can see kind of what happened. Was it a prime number? Was it not a prime number? And we'll do the right thing. Okay, so that's basically it. It looks identical to what we did before, except this implementation uses the Java 7 or Java 5 versions based on FutureTask rather than the one that used Java 8.